Yeah, welcome from my side. I'm happy to present today our CESAR-P modeling tool, and I will explain you in a minute what it is about. So CESAR-P stands for Combined Energy Simulation and Retrofitting. And the P comes from that it's programmed in Python. And it's basically a software which evaluates the energy consumption of buildings and also allows you to assess various retrofitting strategies from the building level up to whole neighborhood cities. And we used it also already at the national scale. CESAR-P was developed by our laboratory, so by the Urban Energy Systems Lab at EMPA, and it builds strongly on a tool which we developed when I was still at ETH at the chair of building physics, which was called at that time CESAR. CESAR-P is in Python and CESAR was programmed in MATLAB at that time. So why did we start, or why is it useful, this tool? If you want to assess or implement renewables in districts, you have to know something about the demand. And usually, if you want to know that at the district scale, it's usually difficult to get demand profiles from individual buildings within a district. And we use this opportunity to develop simulation where we can assess the current energy demand of buildings, so make a prediction basically how the demand is at the current state. And we can also use then these simulations further to predict, okay, how does it, could it change in the future if we apply certain retrofitting strategies? And you see here now a picture where we mapped it on different buildings in Zurich. That is the situation in 2015, where red buildings have a very high energy consumption until low, shown in green. And we can use then this tool to predict in the future how this demand could change. So buildings get retrofitted. Now, assuming, for example, a business as usual scenario from the energy strategy, or we can also use other strategies where we, for example, have the new energy policy, how the demand is changing until a certain time in the future. So how is CESAR-P developed? It is basically a bottom-up building stock modeling tool where each individual building is modeled. And it takes also the shading, the surrounding into account, so shading objects. So for example, if you model a city, then you have also all the other buildings modeled. How we do that is by using 3D geometry data, which are processed. And we are generating for each individual building a simulation model. And you see here now on the bottom, the red building in the middle and then the surrounding objects. So it basically builds an Energy Plus file for each building, and then it jumps to the next and takes always this surrounding shading into account. As already mentioned, it's programmed in Python, and it uses as a core the simulation tool Energy Plus, which is quite a well-known building energy simulation tool, which has all the building physics taken into account. So you have conduction through the wall elements modeled, you have convective processes, you have radiation processes taken into account. And the nice thing with using a already well-established tool is that it's always further developed, and you can quite easily update then also your urban simulation with a newer version of this Energy Plus, and go also more into detail if you want to model a building more in detail. We have connected CESAR-P to various databases, which you see on the left side as an input. So we use, for example, different climate data. So there are ready-made weather files for certain locations, which you can use for the present, but you can also use future weather files. So for example, climate change taken into account. We have also connected it to 2.5D geometry data from Swiss Topo at the moment, which allows you to model for every building now in Switzerland, the energy consumption. And additionally, also we take different building characteristics into account. So when is the building constructed? So based on the construction year, we take typical archetypical constructions for the certain periods. We also take into account different use profiles, so based on what kind of building it is, if it's a residential building or an office building. So there are all kind of schedules also integrated. Regarding the output of CESAR-P is that, as I said, we model each individual buildings, and you can then, you see here now an example on the right side, use this, show these profiles for each individual building. Here, for example, the heating demand for every hour of the day. So we can model heating, cooling loads. We can also model indoor temperatures under certain conditions. We can model the domestic hot water demand, the electricity consumption, and we can also process some comfort parameters. So we could, for example, take different comfort theories into account and assess if a building is at a certain stage within comfortable limits, or if you would have to heat or cool. We also can then already implement different retrofitting strategies by insulating different elements of the buildings, walls, windows, and so on, and use this then to come up with certain strategies into the future. So for example, assume a business as usual scenario where 1% of the buildings get retrofitted each year, and we can assess then how the demand is changing over time. So for example, 2015 to 2050, for certain districts under different scenarios. We can also output operational costs and emissions. So we also have costs for retrofitting taken into account, and also the embodied emissions of the different retrofitting strategies, and also the investment costs. Regarding the spatial and temporal resolution, at the moment it covers whole Switzerland. It is quite easy to do that also for other countries, but the current databases are valid for Switzerland. The spatial resolution is at building level. So you see here, for example, different neighborhoods for what we have already, which we have already simulated. So urban, suburban, and rural. That was also how we have initially planned to use it. But later on, we also figured out it's quite useful to run scenarios for the whole national building stock. And there we don't want to simulate all the 2 million buildings which are in Switzerland, but we use there usually a clustering approach where we cluster the different buildings into typical clusters and then model only specific buildings. So that's also a way how you could use the tool. Temporal coverage is dependent on the weather files. So if you have weather files for any kind of year, past year, future years, you can use that for the simulation. Temporal resolution is that we model usually at an hourly time step, but in the background, it actually computes it or solves it basically every 10 to 15 minutes. So you could also have the output if you want at 10 to 15 minutes. Sector coverage is space heating and cooling, domestic hot water and electricity. And we cover, meanwhile, already all the different building types. So residential, office buildings, industrial buildings, and so on. I will give you now a couple of examples how we have used CESAR-P in the past, by starting now with a short overview on basically where we wanted to evaluate for certain districts what is the current energy consumption and how could that change in the future. You see here depicted now these 3 different case studies with buildings shown from the different, which are constructed in different time periods. And key outcomes are that I showed already. That's basically the transformation of the energy consumption according to the Swiss energy strategy for this certain district here now shown until 2050. Additional results which we could show is, for example, we could now say if we retrofit now under certain, for 2 different scenarios, so the business as usual or the new energy policy, and we have to retrofit, what are the relying investment costs? So for wall retrofits, roof, windows, and so on. Another useful output is then also that we could show how the heating systems shares are changing. So we have certain systems in 2015, and for example, we get then more heat pumps over the years in certain buildings, and we can then basically show that for the whole district what the share of the energy carriers or the systems will be in the future. That brings me now to the second project where we have used CESAR-P. I mentioned already we used also a clustering approach. So for one of our projects, we wanted to identify what are optimal retrofitting strategies for Swiss buildings. So what are the most useful strategies in order to reduce the CO2 emissions in the future. And we wanted to do that for the whole building stock, and we came up with 500 single and 500 multifamily clustered buildings. So these are actual buildings which we simulated, and all of these buildings, so all other buildings basically could be associated with one of those buildings. So you can use this then for upscaling to the national building stock, to this 1.8 million buildings here, which are existing residential buildings which are existing in Switzerland. And I should just show you one result here. So basically what we did is that we used CESAR for the demand simulations, and then coupled that with an energy hub optimization tool, similar to the one to the eHub tool, which Andrew Bollinger already presented some time ago, and identified what are the optimal solutions in order to meet the criteria of the SER and Effizienzpfad Energie, which basically is following the 2000 Watt Society. So you have to have a certain CO2 threshold, which you have to meet for the operational emissions, but also for the embodied emissions. And you see here now those solutions highlighted. So you see here, for example, the split of systems. So what you would have to install now in all the buildings, or what be the optimal solutions for all the buildings to be integrated, and at the same time also what envelope retrofitting strategies you should target. And what you could see is also that not all buildings have to be retrofitted, but you would, for example, 20% of the buildings would also be sufficient if you don't retrofit them in the future. Another project where we used it is because we are using this energy simulation tool, Energy Plus, in the background. I mentioned already that you can go more into depth if you want to model something more in detail. And what we wanted to do in this project is that we wanted to evaluate how is the energy demand changing of buildings for cooling in the future if we take various climate change scenarios into account, and what is the potential for reducing the overheating in the space with passive cooling strategies. And these are, for example, if you use night ventilation, so opening the windows at night, or if you have window shading. And also for that, we used the clustering approach. So clustered the whole building stock into typical buildings. Some are shown here. And key outcomes, you see here now a picture on the right side where you have the base cooling demand in 2050, and then how it would change if you, for example, would use now night ventilation or shading, or a combination of the two. And the last project which I would quickly like to show is we also had a project funded by SFV, which was called Staverdi, which evaluated densification strategies for neighborhoods in cities. And we wanted to evaluate what is the impact on the energy use if you densify. And what we at that time didn't have in CESAR-P is that we could only evaluate what the embodied emissions of retrofitting strategies are, but not for the whole construction. So we added that additionally. And you see here now some examples. So one example for a district where you have a district just retrofitted. So you see here now what is the total energy which goes into the operational energy for heating and cooling, and the embodied emissions which goes into into the retrofitting. So if you just retrofit it, or if you densify the district, just a little bit of densification or really high densification. And we had also different scenarios in this case. So one was really a tabula rasa approach. So you tear everything down and rebuild everything. And the other is that you keep as much as possible and just try to add additional floors, for example, and buildings in between. And what you see quite nicely here is that actually the operational energy is in that sense only half of it, and the rest is in the embodied emissions. And so it really makes sense that you try to keep as much as possible, because if you would do that, then you can reduce the embodied emissions quite significantly. And we also evaluated what the timber strategy compared to a concrete strategy would be, for example. So this is also an example how you could use CESAR-P. Okay, that was a bit how you can use it. Now a couple of slides on the architecture of CESAR-P. So it's quite a modular structure, which is managed by individual YAML files, config files, where you see here some examples here. And CESAR-P is combining them basically. And you see here on the right side also for example, what parameters you could change. So the radius taken into account of the building, how many buildings should be still simulated if you have your main building in the middle, building heights, and so these are parameters which you can change. So it's quite easy to adapt certain things. And the process, how that works is that first a building model is generated by this approach, which I showed already before. Then you can have a retrofitting selection. Then it basically runs Energy Plus in the background. And then you have a results processing where you can output then the different results. As input, you need basically the building footprint and the height. That's this 2.5D. So we take the footprint and the height into account. Then the year of construction. Then what building type it is. You can also use then an hourly weather data file, or you have to use, which is in the format EPW. And then also for shading, the footprints and height of the neighboring buildings. And all this input data for Switzerland, we have that already predefined. So you could just basically by defining the coordinates of a certain building or saying which building you would like to simulate, you could do that for every building in Switzerland automatically, because the data are already implemented. As an output, you get then annual demands, space heating, cooling, domestic hot water, electricity. Additionally, you could also query hourly demands, and then operational emissions. You can operational costs and emissions you can get as an output, the different retrofitting measures, and then also the associated costs and embodied emissions. A bit about the geometry creation. So how it works is that, as said already, these footprints we take into account. It basically builds up these vertices automatically and then takes a building height into account. We then also define typical glazing ratios. That's usually something also what is not easily accessible, which information. So how we do that is that we, based on the construction year, assume a certain glazing ratio, which we can then also vary between different buildings so that not every building has the same glazing ratio. And we also take the adjacent buildings into account. So if it's a freestanding building or if it's adjacent really to another. A bit about construction and the operational properties. So we assume, based on the building age and the building type, we take a Swiss standard into account, which is called SCR 2024, to define the use profiles of the different buildings. So if it's a residential building or an office building, you have then basically different use profiles in the background. Depending on the year of construction, which you get usually from, for example, if you use GVR data. This is the housing registration data of Switzerland. So every building is registered in Switzerland, and for each building we know when it is constructed, how many people live there, and what it uses as an energy carrier. And we use this information in the background of CESAR-P to get some archetypical information. And for example, we used it for the construction. So we know a building is, for example, constructed in 1960. And at that time, a typical construction of walls and windows looked like that. And we assume this as an input then for our simulations. Then regarding the operation and the occupant behavior, as I said already, we take this standard into account, this SCR 2024, where we know, okay, we know the number of people in a house, and based on that, we know also what are the preferences for heating and cooling schedules, temperatures, and based on that, we can then also have a schedule. We take the lighting and all the electrical appliances into account, and the profiles based on that. And additionally, we can then operate certain things, like we can assume certain shading strategies for our windows, or assume night ventilation and so on. So this is then quite free to also add different features to CESAR-P, depending on the question which you would like to answer. All the information is stored in building containers, where you find it's automatically set up by CESAR-P, where you have the building model, all the results, and also all the assumptions documented. And that is quite useful if you want to run then later on CESAR-P again, and for a different analysis, that you can build on that information already from a certain case study, for example. Regarding the retrofitting, so each building and each element is retrofitted, treated separately. What we can integrate basically at the moment, we have the roofs, the walls, the windows, and the ground floor taken into account, and we can also run it for combination, so that you, for example, have a full retrofit where all of these elements are retrofitted at the same time, and can be processed. And the good thing, because it's quite modular, you can then also just, for example, run for whole Switzerland an analysis where you could say, what are the embodied emissions, CO2 emissions in a certain construction? So you could say, if I now insulate all the roofs in Switzerland, what would be embodied emissions, for example? So you can run then this kind of analysis as well. Regarding validation, calibration, we have compared CESAR, so the output of the simulations, with energy consumption data, which we had for a village in Graubünden, so Zernetz. So there we modeled all the buildings. And what you can see here is in this table on the bottom is the difference between simulated and measured. That what was actually annual readings what we had. So the deviation is quite small if you aggregate that to the whole district scale, also to the whole village of Zernetz. If you see at individual building level, you can have quite some discrepancies. That's why, or the reason for that is because we use standard assumptions, and of course every person, individual, behaves not as a standard occupant always. So there are some deviations at the building level, but in an aggregated way, it's then okay. And further calibrations are also ongoing. So you see also here that all the newly built buildings, we underestimate quite significantly, and we are trying now to adapt that so that it matches more to the measurements. Limitations from CESAR-P are at the moment that the databases are currently only available for Switzerland. And the geometry input is only in 2.5D, so basically the floor print of the footprint of the building and the height. So the roofs are assumed to be flat. And each floor is just modeled as one zone. So in Energy Plus, you could model all rooms separately. So you could go in much more detail. But if you want to run that then at an urban scale, that's quite a limitation in terms of modeling time. So that's why we assume just one zone, but that's also something what could be adapted. And we are also currently working also on more advanced geometry input that we also go to really 3D data, then taking also the roof geometries into account. And another limitation is that we have no user interface. So it's really just a text-based input. This is because we just use it for research. We have no intention at the moment to commercialize it. And that's also why we haven't worked on a user interface at the moment. Linkages to other tools in Pathfinder. How we have used it in the past is that we have a link between CESAR-P and the eHub tool or other Energy Hub versions, which we also have in our lab. So basically we use CESAR-P for the energy demand calculations, and we use this then as an input for the Energy Hub optimization. And potential other links would be in the project. You could, I guess, also couple that to similar approaches for Nexus E, Calliope, and also Remap. So basically use the energy demand inputs from CESAR for these other tools. Further development under the Pathfinder project, what we have identified, it's still under discussion if we really do that, but that's something what we could suggest, is that for work package 1, we extend the scope of CESAR-P also to other European countries, for example, by building also on an archetypical approach and derive then demand profiles for the other countries which are relevant within the project. Another thing what we have discussed is that we integrate also demand flexibilities in CESAR-P. So basically what we could play with is at the moment we assume a certain temperature for our set point temperature for our heating system. And we could play with this temperature bound, so still within the comfort limits, and assess the demand flexibilities. That would be something what would be for work package 2 and also interesting for work package 3. And what we are also updating, I mentioned that already, is that the geometry, we are currently working on direct import of CityGML data. So this is already quite available for quite some areas where you have then more in detail roof geometries and building parts taken into account. Current uses is basically it's researchers in the field of energy system modeling. That's what we know. So we use it quite intensively in our laboratory, but we also know other researchers are using it. And we have also released an open source version of it, so it's freely available. So everyone who wants to use it can also use it. Potential users would be also, I think it could be interesting for cities and communities to get more detailed pictures on their energy demand at the moment, but also on strategies to develop strategies in the future. And also, of course, consultants for energy system planning. There, I would also see potential for the future. So CESAR-P, I mentioned we released it quite, I think, a couple of months ago as an open source license, which you see here. So it's basically this Affero general public license, which we released it. You find further information on the software on our webpage. The source code is available on GitHub. We have also a documentation, also here a link, and also a download also shown here. I want to quickly also mention there are a lot of contributors to CESAR-P and CESAR from our laboratory and also from ETH over the past. So a lot of people are contributing, and I think it's still an ongoing process. So we are still working on improving the tool. And yeah, that was it from my side. Thank you very much for your attention, and I'm open for questions if you have any.